turn it to Yangyang Wang now from University of Iowa. And take it away, Yangyang.
Thank you for the invitation and for the introduction. So I'm going to talk about shape and timing perspective of using this variational analysis to dissect motor robustness. I'm going to start with some key questions in motor control. One of the remarkable feature of motor control is that behavior are both robust and flexible. And by that, I mean by the robustness, I mean the ability of the system to maintain its performance despite perturbations, and flexibility is that the system is able to deploy alternative strategies to improve fitness. So it's important to understand this robustness and flexibility and also the roles of sensory feedback and biomechanics. In today's talk, I'll focus on understanding robustness and try to understand what roles the sensory feedback and biomechanics are playing here. So to do that, to dissect motor robustness, we need models for given biomechanics control systems. And then with the model, we can define test fitness, or what we can call that performance. Once we have that, we can apply perturbations. And here the perturbations I'm considering is small. We apply perturbations that's gonna potentially change in both timing and shape of the limit cycle system, which will then together influence the performance. Then we ask how much the performance changes due to this perturbation. So because both shape and timing of the limit cycle have changed under the parametric perturbation, so we need tools to track both changes. And then with the tools, we can determine what factors contribute to robustness and how they contribute. So this is the approach that we are going to use. And the kind of system I'm going to consider is the feeding behaviors of the sea slug aplysia. Okay, so aplysia is a type of sea slug, and it feeds on seaweed using an organ located in its head called the buccal mass to pull the seaweed into the mouth during the feeding. And here the movie showing here is showing that an aplysia swallowing a seaweed, and also a cartoon here. And the perturbation that we apply here is on this seaweed when the animal is swallowing the food, a small mechanical perturbation. The ingested behaviors of this system can be decomposed into three phases. One is the protraction open phase. That is saying the animal, the grasper, is opening and protracting to reach the food. And then it closed on the food while still doing retraction. So that's protraction closed phase. Then it pulls the food back to the mouth. That's the retraction while it's closed on the food. So during the retraction closing phase, the animal is swallowing the food. So this is the system we're going to consider. And here is the a cartoon showing the three different phases. Corresponding to them, there are three neuron pools. A0, A1, A2 represents the firing rate of these three neuron population, and they are mutually inhibiting. So this term represents the sensory feedback depending on XR, which is the grasp position. This neuron population, activation of this neuron population will activate some muscle activation. For example, A0 and A1, corresponding to protraction open and protraction closed, will activate U0, that's the protractor muscle activation. And A2, that's the retraction closed related to neuron population, will then activate U1, that's the retractor muscle activation. So these two muscle activation together will generate a force that we denote as F sub muscle. This force will move the grasper position XR either forward to reach the food or backward. So then the animal is following the food. FSW is the experimentally applied mechanical load. And this, because this perturbation, as I said, is applied on the seaweed, so it can only be felt by the system when the grasper is closed on the food. So therefore, it's multiplying an indicator function R, which is 1 when the grasper is closed. And that is modeled here as the total activation of the protraction, open protraction, closed neuron activation be larger than some threshold. And then if it's smaller than these thresholds, then it's open. So then with appropriate parameters in the swallowing mode, the system can generate heteroclinic cycle. And here I'm showing the projection of that cycle into the 3 neural muscle phase space, shown by this black trajectory. And these 3 walls represents the hard boundary that we call hard boundary here. These are given by these 3 firing rates of the neuron activation being 0, because they represent firing rate, they cannot go negative. So we have 3 hard boundaries, and the yellow surface represents this opening and closing boundary. That's a transversal crossing boundary. When the trajectory is below, the grasper is open. When it switches above, the grasper is closed. But together we have 3 hard boundaries and 1 transversal crossing boundary. This is a piecewise smooth system. Now we can define the task fitness. In this swallowing behavior, task fitness can be simply defined as the averaged CVIT intake rate. So that's total amount of the CVIT consumed divided by the total time. And we want to express this using the model variables. Here I'm showing the time trace over a cycle of this grasper position. Shaded region represents the grasper is closed. And we can see that this part is protraction open and then switches to the shaded region that's protraction closed. Then after some points is doing retraction. XR is decreased, meaning that the animal is intake the CVIT, is intaking the CVIT. And here we don't have the CVIT intake explicitly shown in the model, that I didn't show in the model, but is modeled as assuming that the CVIT is moving together with the grasper when the grasper is closed on the foot and not moving at all when the grasper is open. Okay, so then with this, we can then represent these task fitness using these variables. Basically, the total amount of the CVIT consumed per cycle is the net change of the CVIT intake, or the net change of the grasper position. So that's the minus delta XR and divided by the period, for one cycle. With this, we can then quantify task fitness by applying different perturbations. And here, this is the perturbation on this first neuron population. That's the sensory feedback gain term as we increase it. And here is the mechanical load as we increase the load applied on the CVIT. And for today's talk, I'll focus on this direction. We will increase the load on the CVIT and then study the robustness and also the underlying mechanism. And we can see that as we apply these perturbations, the task fitness does not change much. So that's indicating the strong, relatively strong robustness. Okay, so, and then before we study that, I'd like to give an overview of these methods. And we apply perturbation, as I said, is a small perturbation, so it's different from what Dan talked about. And therefore, to study changes in the timing, we are going to use the standard phase reduction, and then already introduced that method. And here, I want to mention some other limitations of this method to be able to apply to our system, is that this method is well developed for smooth systems and also has been extended to account for transversal crossing boundaries, but not necessarily the hard boundaries. And we have the hard boundary. So we extended this method further to for systems with sliding components or with hard boundaries. And also this method is very good at measuring the timing sensitivity, but only the global timing sensitivity. If we want to know how the duration of the time within a specific region changes, for example, during the closing phase changes, then we will need to use another tool that we developed, and that is called the local timing response curve. And then to check the changes in the shape, we will use the classical variational analysis. And also some limitation here is that over time, shapes of the original trajectory and the perturbed trajectory will then become increasingly out of phase. And to overcome that, we developed what we called infinitesimal shape response curve. So later I will give a little bit more details to these methods for us to check the changes in both timing and shape, which will then help us understand how the performance changes and hence understand the mechanism underlying the robustness. Okay, so first this IPRC, as Dan said, we can reduce our oscillating system to a single phase equation, theta, and equals to this one. We here is rescale differently. So instead of the intrinsic frequency omega, here is just 1, and then plus infinitesimal shape response curve multiplying an external perturbation. So this infinitesimal shape response curve IPRC, when it is positive, that means a perturbation arriving at that phase will lead to a phase advance. If it's negative, then that will lead to a phase delay. So this curve will tell us the timing sensitivities to all kinds of perturbations. Then with this, we can then apply these to our system to understand the timing sensitivity. And this for an asymptotically stable limit cycle, one can show that IPRC can be written as the gradient of the phase, and it satisfies the adjoint equation between switching boundaries. At the switching boundary, because F is not smooth, so dF is not defined, therefore the IPRC will experience a jump on the switching boundary. And for the transversal crossing boundary, this paper characterized how that jump can be captured by a jump matrix. For non-transversal crossing boundary, that formula no longer applies. So then in this paper, we characterized the jumps of these IPRC near the non-transversal crossing boundary. In our case, that includes the landing point when the trajectory lands on the hard boundary and then forced to slide along the hard boundary until it naturally lifts off the boundary. And interestingly, what we find is that the IPRC does not have any discontinuous jump when there is a hard landing here. It changes continuously, and moreover, the normal component of IPRC continuously decrease to 0 and remain 0 on the hard boundary. At the lift-off point, however, it experiences a non-zero instantaneous jump, and it cannot be captured in forward time, this jump. So we defined a time-reversed version of this jump matrix, which will then capture the jump from the IPRC immediately after the lift-off point to the IPRC before the lift-off point. That's by this script J, captured by this script J. So basically, that is given by this formula, which is saying that as we go backward in time, the normal component of IPRC will discontinuously jump to 0 and remain 0, and nothing discontinuous happened here. Okay, so then with this being captured, we can then apply to our system. On the top trace, I'm showing the time series of the model variables over one cycle. Top left panel shows the neural variables, and this is the muscle activation and also the grasper position. Bottom shows the IPRC corresponding to these curves over one cycle. What I want to point out here is that the IPRC is they are continuous except near these lift-off points, as I showed in the previous slide. This is where the lift-off events happen. And moreover, so this is basically telling us that perturbations on the neural variables, they do not have a big effect on the system, on the timing of the system, unless they arrive at the right timing, shortly after the lift-off events. For this talk, because I'm considering perturbation on the grasper, so I actually only need to look at this curve. That is the IPRC corresponding to the perturbation on the XR, on the CVIT. And because the perturbation is only exists when the grasper is closed, so we only actually need to look at this portion of this yellow curve. And we can see that is below 0 is negative, meaning that perturbations to this variable will give us phase delay. So that will prolong the period. And we can integrate, let this curve times the perturbation and then integrate that over this closing phase that will give us the estimated value for the linear shift in the period. And we can then plot them. It agrees pretty well with the numerical result. And as shown here is saying that as we increase the applied load on the grasper or on the sieve, the period is prolonged, is getting larger. So this is telling us the timing sensitivity to this perturbation that we considered. This is the perturbation. Next, I want to consider how the shape of the limit cycle changes in response to the perturbations. So that's shown here. We have, because we applied a sustained perturbation, so that's or you can think of that as the parametric perturbation. Now with the perturbation, we have a new limit, we have a new vector field denoted here by F epsilon, and we have a new limit cycle denoted by gamma epsilon. And this has a different shape compared with the original periodic orbit. Again, this is the perturbation that we applied. So then this gamma 1 is the linear shift in the shape. And here I'm plotting the perturbed trajectory denoted by the dashed curve and unperturbed trajectory that's denoted by the solid curve here. Again, this is the neuron variable, this is the mechanical variable. And then when we subtract them, the difference between them are shown below. And these curves are actually solutions to this variational equation. So they can be found by solving this variational equation. And here the non-homogeneous term arises from the perturbation acting directly on the vector field. Okay, so this result, if you look at this panel, it can tell us several important insights. First of all, I want to mention that this curve, that is the displacement on the grasper position, is increasing and is positive. So this is saying that this is because the grasper is getting pulled by a larger force. So it will be pulled further. Therefore, it's positive. And these positive changes will then immediately be propagated to the neural variables through the sensory feedback. XR changes on XR will be felt by the neural variables. However, we do not see, as we can see, we get a big changes in the XR, but we do not see any changes on the neural variables. And this is because of the hard boundary effect that I talked about before. Hard boundary effects are delaying the effect on of the sensory feedback. Until the lift-off point, then we see the positive bumps on this A2 neuron population. That's the retraction neuron population. And this positive displacement occurs when this neuron is deactivating. So the positive displacement here is suggesting that this neuron population is now turning off at a later time. And therefore, this neuron pool is activated for a longer time. And because of that, more retractor muscle force is built up. So we get a positive displacement here. And in contrast, we have a negative bump in this protraction open neuron population. And therefore, that leads to a decreased protraction muscle activation. So then together, the changes on these two muscle activation will then change this force generated by the two muscle activation. And what happens is that this term, which is already negative, later in the retraction cycle will then become more negative to overcome the increased load that we applied here. And here I'm showing the displacement of this term. So you can see that after the sensory feedback effect kicks in, it becomes more and more negative. One last point I want to make is that before we see the sensory feedback effect somewhere here, this is already negative. So that's suggesting the system is already doing something to overcome the increased applied load. And because we do not see any changes in the neuron variable, so that has to be due to the biomechanics and purely due to biomechanics. To understand that, we will need to look into this further. And for the interest of time, I will skip that. Okay, so this, while this is helpful in explaining some of the mechanisms here, it is still incomplete. And also I want to mention that over time, this becomes more and more inaccurate because the perturbed and unperturbed trajectory actually becoming increasingly out of phase because they have different periods. And also what I didn't mention is that this is indicating the transition from closing to opening for the perturbed system. And you can see this is also being delayed. So because they have different timing, they become increasing out of phase. Therefore, this will become not as accurate as time increases. So to overcome that, we want to introduce a method that we can actually rescale time so that we can compare them at corresponding time points. And to do that, we then introduce a rescaled perturbed time denoted by tau epsilon p. And then this new gamma 1 is what we call the infinitesimal shape response curve, which satisfy the following equation. These two terms are exactly the same as before, as the right-hand side of the variational equation, except now we have a new non-homogeneous term arising from this timing rescaling. If we want to rescale time just uniformly, assuming the system has a uniform timing sensitivity to the perturbation, then that is given by this relative shift in the period, which can be estimated from the IPRC. And then we get a uniform ISRC with uniform rescaling. However, in some cases, we may have different timing sensitivities to perturbations. For example, in the aplysia system, the perturbations only exist during the closing phase. So it is natural to expect that perturbation has different impact on the timing sensitivity during the closing phase versus during the opening phase. So for that, we may need to use different mu1s, this term, in different regions, depending on what system we have. And that will then lead to a piecewise uniform rescaling if we rescale timing differently in different regions, and that gives us a piecewise ISRC. In different regions, we have different mu1. And to get this mu1, then IPRC no longer works because it only gives us the global timing sensitivity. So then we will need to use the local timing response curve. And this is analogous to the IPRC in the sense that it is defined as the gradient of the time remaining until exceeding this region through some exceeding boundary. And it also satisfies the same adjoint equation satisfied by the IPRC, except it has a different boundary condition. So now in different regions, we have one piece of this LTRC that can estimate different mu1. And here are the results. Now we can see the opening and closing events, they coincide because of due to the timing rescaling. And then again, if we want to focus on this yellow curve that's corresponding to the displacement of the retraction neuron activation, we see both positive bumps when this neuron is activating and deactivating. So that is again indicating that we have a longer retraction activation time. And here, because we rescaled time, so by longer, I mean longer percentage of the cycle, this neuron is activated. And that gives us a stronger retraction muscle force. Therefore, that will pull the displacement of the XR down below to be negative. Sorry about the noise. And here, when the grasper is opening again, the changes in the XR is negative, meaning perturbed XR is more retracted. That means the animal is actually swallowing more food to overcome the increased load. So that is saying the system basically compensates this load increase by prolonging the retraction phase, which allows the retractor muscle to build up more force to digest more food. Okay, and that agrees with the experimental results, which shows that the duration of the retraction muscle, retraction neuron is getting prolonged with due to the increased load, but nothing really happens for the protraction neuron. And one last thing I want to mention is that with these tools, we can also quantify robustness. Just remind you, this is the tested fitness. And in this paper, the authors show that these the relative changes in the task fitness per perturbation can be decomposed into two parts, and these two parts can be exactly be estimated using the ISRC and also the IPRC. So we can estimate these two terms, and therefore we can actually use our estimated value to plot how the relative reduction of the task fitness changes over perturbation, and it agrees pretty well with the actual with the numerical results. And to interpret this better, I'm plotting the same data, except here I'm plotting epsilon over FSW. So that's representing the relative increase of mechanical load. And if we pick a point, for example, here, that is saying a 42% increase on the mechanical load leads to only about 0.5 reduction in the task fitness. So that's how we interpret this robustness. And just to show that if we use the uniform timing rescaling, then we do not get an as good approximation when we quantify robustness. So to summarize, we used this variational analysis to show that biomechanical properties actually confer resilience by immediately increasing resistance to applied load on a timescale much faster than neuron responses. And neuron sensory feedback effects on these neuron activations are largely delayed by firing rate hard boundaries. And the main effect of the sensory feedback is through shifting the timing rather than changing the magnitude. And also our analysis of using the ISRC and LTRC provides a more accurate and self-constant description of the changed shape and better understanding of the robust mechanism, and also provides a way to analytically quantify robustness. So some of the future work here that we can study robustness to other perturbations, and also using the method to apply to other limit cycles with transversal crossing boundary or hard boundaries. This is a coupled stick slip oscillator. It has hard boundary corresponding to the sticking phase. And we can use our results to actually predict synchronization of such systems. And also thank my collaborators, Peter, Hilo, and Jeff. Okay, thank you.
Thanks, Yangyang. Questions for Yangyang? I see Mustafa S. has a question. Go ahead.
Hi. So you showed the jump condition for this sliding solution in slide 8 or 7 somewhere. So is this just ad hoc for your system, or can we apply this for general sliding?
For general sliding
Yeah.
condition. Somewhere
8 or 9 or somewhere there.
Yeah, here, this one.
Yeah.
This is for any finite dimensional limit cycle system that experience. Yeah.
Is there any relation between this jump in the IPRC, and jump in the solution of this variational equation?
In the transversal crossing, there is like a relationship, but for non-transversal crossing is a different kind of relationship, and we cannot define forward jump. We can only define the backward jump, so it's kind of different. Actually, in the variation analysis, it's totally opposite. That discontinuous jump occurs at the landing point. The normal component becomes 0, but nothing happens here.
Okay, thank you.
Thank you.
All right. And any others? Maybe I have time for one quick additional question. All right. Well, if not, thanks again, Yangyang, for a very detailed and yeah, really nice set of mathematical analysis.